start out with homework questions. Who's got what? Any problems anybody wants to see? Got to be at least one or two. None?
I was a little confused on like the meaning of like a rectifiable curve.
Rectifiable curve. First of all, it means one piece and no pointy places in it. Right? Its definition, it's a differentiable curve. So everywhere on that curve, there is a derivative, or there is a non-vertical tangent line.
Oh, okay. Thank you.
It's basically what it means. Yeah, math definitions are, it's like reading a lawyer's paper, right?
Yeah.
Yeah. I didn't use that word in class because, you're not going to be given problems that can't be done. So if you remember from Calc 1, if you've got a function's continuous, then that means every x has a y, right? But a function to be differentiable, you can be continuous and have a point, but you can't do a derivative at the point because the limit's different on the left and the right. So rectifiable, just think of the word smooth and unbroken.
Okay, thank you.
Yep, that's good enough.
Could we go over number 40 from page 474?
Sure can. Number 40. Let's see here. That's the 3x one?
Yeah.
Yeah. Sometimes a problem can be like so simple and straightforward, you tend to overthink it and think it's a lot harder than it really is, right?
Yeah, I don't even think you had to do U substitution on this one, but I tried to, and I think I just confused me.
No, you don't. In this case, it's a problem that becomes so, I don't want to use the word simple, but I'm going to use that word simple, and you keep thinking, I don't know,
Yeah.
You get suspicious. So number 40 is y is equal to 3x, and we're going from 0 to 3. Okay, so y equals 3x. Well, x has an exponent of 1, so it's just a straight line, and the 3 just means it's tilted up. The number, if you have x to the first, remember the number in front is the slope of that line. So it just kind of looks like this. Oh, doesn't look anything like that. And this would be 3, and this would be 9. Right? And we're going to spin that, we're going to spin just the line around the x-axis. Now, if this question was about volume, so when that spins around, it's going to look like a sideways ice cream cone. Just going to look like a cone. We could use the disk method to figure out the volume and arc length to do the length, but you don't even need calculus to do that. So this is just, when this spins around and makes that ice cream cone, how much paint to go around it, right? So we don't really even need the picture here. So the first step is we do the derivative, and that derivative is 3. The next step is to square the derivative, and that gives us 9. Then we go right to the surface area formula. So the surface area is 2 pi. We're integrating from 0 to 3 because that's what the problem gave us. In the surface area formula, the function goes here. And then we use the square root from the arc length thing. And the square root is 1 plus y prime squared. So there's the setup for the integral. So I'm going to pull all the constants out in front. So 1 plus 9 is just 10. Right. So 3 and the square root of 10 are constants, so you can pull them right out in front. So this will give us the surface area is 6 times pi times the square root of 10. And we're going to integrate from 0 to 3, just x dx. So there's the integral. So all those constants and stuff make it look confusing. All right, any questions yet? I'm going to erase this stuff so I have some more room. All right, so the integral of x is 1/2 x squared. So our surface area becomes 6 times pi times the square root of 10, and then 1/2 x squared, whoops, and we are going from 0 to 3. This 2 can cancel out with the 2 inside the 6. So our surface area will be 3 pi square root of 10. The 3 goes in first. 3 squared is 9. The 0 goes in second. That's 0. And so this 3 times 9 is 27. So we get 27, oops. We get 27 pi times the square root of 10. And that's the answer. And the units on that would be units squared. So inches squared, centimeters squared, whatever squared. And that's that one. So that one probably looked a little confusing because you got the pi, you got the square root of 10, you got all that stuff going on. What else? Any of the other problems?
Professor?
Yeah.
I had a problem with one of the questions that I don't think it was on the homework, but I tried looking it up because I couldn't solve it. I was wondering if you could go over it with me.
Sure. Well, first, anybody have any from the numbered ones yet? And we'll come back. So is it surface area, Sean?
Yeah, it
Okay.
was question. So it was like y equals 1 over x plus 1 between 0, x is between 0 and 1.
Did I get that right?
Yeah, that's it.
Okay. So we have to do this derivative, right?
Right.
All right. So I'm going to rewrite this first to do this derivative. So I'm going to rewrite this as y times x plus 1 to the negative 1.
Right.
All right. So we do this derivative. Negative comes in front.
Mm-hmm.
Subtract 1. Chain rule derivative of the inside is just 1, so we don't need to write anything down. So our derivative looks like this, negative 1 over x plus 1 squared.
Right. That's what I got so far too.
Okay, so that's the derivative. Oh, sorry, derivative. Right there. Now we have to square that. So the derivative squared, the negative goes away, and this turns into a 4. And that's the derivative squared.
Right.
Okay, good with that?
Yeah.
All right, so now we put it into the surface area formula. There's a 2 pi out front. We're going from 0 to 1. Put the function in. And then we put in the square root expression from the arc length formula, which is 1 plus 1 over x plus 1 to the 4th. So that's everything into the formula.
And do you then unfoil that out or whatever, and then or cross, like multiply?
No, I'm not going to foil anything out. I'm going to leave it in that form.
Okay.
In general, well, there's no always. It's usually best to leave things compact, but sometimes you have to foil out to get things canceled. But yeah, there's some algebra that happens now. So I'm going to change this 1 into x plus 1 to the 4th over x1 plus 1 to the 4th. So I'm going to write the number 1 this way. Right? Now they both have that common denominator. And we're under the square root, we will get x plus 1 to the 4th plus 1 all over x plus 1 to the 4th dx. Good?
Okay. So far, so good.
Far so good. Now I'm going to use this property again. I'm going to break this square root up into 2.
Okay.
Okay? So that will give us this. So the square root of x plus 1 to the 4th is x plus 1 to the 2nd.
Right.
Okay? So rewriting again. Rewriting this again. X plus 1 over 2, and here's 1 here. So that gives me x plus 1 to the 3rd power. Because I have this one times this one.
Mm-hmm.
And then we have this. And that brings us down to this. You get that far?
No, I didn't. I kept foiling it out. I kept messing up with that. So
Well, that got really ugly really fast, didn't it?
yeah.
It did. All right. So you foiled, you did this one and multiplied it all out?
Yeah.
Thinking that something wonderful was going to happen?
I thought something would cancel.
Yeah.
I'm like,
No. And it just, all it did was get ugly.
it did. I was like, I don't want to do this.
Yeah. So I'm going to do a U substitution on this one. And then I think you'll see what's going on. So that's my U. So U is equal to x plus 1 to the 4th plus 1.
Okay.
Now we do the derivative of both sides. The derivative of 1 is 0.
Mm-hmm.
And this is a chain rule. So the 4 comes down in front. Subtract 1. And then the derivative of the inside is just 1. So that gives us dx. And let me think here a minute. Oh, hang on a minute.
Would U substitution work here?
This is U substitute. Now I'm thinking maybe it won't.
Yeah, I thought the x plus 1 cubes were going to cancel out, but they're both in the denominator.
I'm sorry, what'd you say, Michaela?
I was saying that I thought like the x plus 1 cubed were going to like cancel each other out, but like they're both in the denominator.
That's what I thought too. That's what I thought was going to happen. This is going to lead to an integral that we don't know how to do yet. By that I mean we haven't gotten to it yet.
So would you just plug this into like a graphing calculator then? And it would.
Oh, good luck with that.
Would you use partial fraction decomposition to solve this? I'm just curious.
That would be good, except for the square root.
Oh, okay.
Partial fraction, and if everybody doesn't know what that is, that's something we're going to get to in the next chapter. But this will lead us to an integral that we don't have a method for solving yet. So wait, what number was this, Sean?
20, I believe.
Is this a surface area problem?
Thought it was.
No, this is an arc length problem.
I'm sorry.
Oh, this is an arc length problem. Ah, yes, this is an arc length problem. That's an entirely different thing.
Okay, all right.
Yeah. So arc length
You wouldn't have the 2 pi.
or this.
Now you can do it.
Well, it's still going to lead us to something that from this. So this was not surface area. It's arc length. And this is not a difficult problem, but the method you need on this one now is something called trigonometric substitution, not U substitution. You put all of this on a right triangle and turn everything into sines and cosines and tangents.
Okay.
It's not difficult from here, but we just officially don't know how to do that yet. I know some of you have seen trig sub before, but officially we don't know that in here yet.
I think I've seen that before where like that turns into tangent or something.
Secant sides of theta, yeah. That's coming in a couple of weeks.
Okay.
And it's not hard. It sounds scary, right? Trig substitution, but it's not bad. So if you got down to this point, you are correct.
Okay. Yeah, I couldn't get past like, I looked it up and they did turn it into like a trig sub, but I don't understand how they got there.
That's because we haven't gotten there yet.
Okay.
It's easy. So this is in a section where the instructions say, get to this point, and then if you can't do it, just stop.
Okay.
All right. It's still a good exercise to go through. All right.
Thank you.
Yeah, sure. Anybody else got anything? Okay. So we're done with chapter 7, except for that pesky little graded thing that's going to happen next week. So I'm just going to randomly just do some problems so in chapter 7, we have area between curves, right? Nothing spinning, just plain old area between curves, which is a holdover from the end of Calc 1. And then we have disk method, washer method, shell method, arc length, and surface area. So I'm just going to randomly make a couple of problems here, either later tonight or tomorrow morning, or later tonight or tomorrow. I'm going to send out a bunch of practice questions on all of those things. Some of them I'll give you the answers to, and some of them may not have them. So this is our virtual start of our weekend. I won't see you again until Tuesday, so you'll have all that time to practice. On Tuesday, we'll go over any questions that you want from anything. And then probably sometime on Wednesday, I will send out the first graded assignment, call it whatever you want. And you'll have about 12 hours to do it and get it back to me. Because I know everybody's got other classes going on and you've got life going on and all that kind of stuff. So we'll go through it on Tuesday. You'll get your questions answered. I'll send it out. You'll have 12 hours to do it. And then you'll send it back to me, not to Canvas. You're going to email it directly to me, and I'll go over all this again. You're going to use your phone or whatever and take a photograph, so you'll have a JPEG file. Or I know some of you have the ability to make PDF files. So JPEGs or PDF, that's all. I can't open anything else. In the past, I've had people send me files of stuff that have weird extensions on the end, or they try to use Google Dropbox or something. So it's JPEGs or PDFs, all right? And I'll talk more about this on Tuesday. Okay, so just gonna throw a problem up here. I'm going to draw two functions on here. I'm going to put pieces of these functions on here. All right, which one is which? Which one is which one? Sine, which one's sine, which one's cosine?
Sine is the bottom one.
I don't,
The
Obviously, the
green
red
would
one.
be the cosine.
there's not really a bottom there.
Yeah, red.
The sine is red. The sine of 0 is 0. The sine of pi over 2 is 1. And that means the other one is cosine.
Don't you have to like flip the signs around halfway through because they'll cancel each other out? Like if you try to do the whole area.
You don't know what I'm going to do.
That's true. I've seen something where it's like I tried to do this and I got 0 because the bottom one sign turns into the top part,
But I don't know what you mean by bottom.
the red one, the sign. So like,
Why is the red one the bottom one?
because that's how a sine wave looks, like the cosine starts at 1.
Oh, I see what you're saying. No, but what I have here is 3 areas. I have region 1, region 2, and region 3.
Ah, okay.
And I'm going to ask you some questions about these. So first question. Should have moved that over. Well, too late now. So question 1. Do the area of region 3. So how do we go about setting up for the area of region 3? Now, area, nothing is spinning around. It's just flat area. How do we go about starting that?
You have to find where they intersect at.
Okay, I found it. It's right there. Where is there?
Pi over 4.
Yep, pi over 4. Yeah. They intersect halfway, pi over 4, and pi over 4 or 45 degrees are where the sine and the cosine have the same value.
Mm.
Okay, that's the first thing we're going to need. Now what?
Yeah, do
Well, there's an integral involved, right?
I think we would do the surface area formula.
Now, this isn't surface area. Nothing is spinning. This is just regular area.
so you have to do integrate from pi over 4 to pi over 2.
We do. So the region we're integrating is this. So we start here and do this. So pi over 4 to pi over 2. Okay.
Sine x minus cosine x.
Top minus bottom. Right. So the integral of just the red curve, just the sine, will give me the area all the way under the red curve. The integral of the green cosine will give me the area under the green. So the area in between is top minus bottom, like we've always been doing. So this will be sine of x minus cosine of x dx. And that's the correct setup for that integral. If we did the area of R1, what would change? If I wanted the area of R1, what would happen?
Cosine minus sine x.
Right. Now, cosine is the top and sine is the bottom, so they would flip and the minus sign would stay there. Okay, good. So we haven't done this in a while. Okay, so now, pretty simple integral, right? So now we just integrate. What's the integral of positive sine?
Negative cosine.
Negative cosine. And what's the integral of negative cosine? Integral of negative cosine.
Negative sine.
Yeah, you knew it was a sine, but everybody's like, oh, I don't remember positive or not. It's negative sine. That's correct. And we're going from pi over 4 to pi over 2. So I'll stop there. So that's the calculus part. Okay. And now we throw some numbers in there. Don't really have enough room here, but that's all right. So when we put numbers in for integral, it's top minus bottom. So we put pi over 2 here. Cosine of pi over 2 is 1 over square root of 2. So we get negative 1 over square root of 2. Or square root of 2 over 2, for those of you who like that. And again, we get that here. Minus, and now we put, wait a minute, I did that wrong. Hold on, I did the wrong thing first. Hang on. Cosine of pi over 2 is 0. Sorry, I was thinking the other one. Sine of pi over 2 is 1, and this makes it negative. Then it becomes negative 1 over the square root of 2 minus 1 over the square root of 2. That's when you put pi over 4 in there. So we get negative 1. This negative, all of these make it plus. And that is the area of that region. In the parentheses here, you get negative 2 over square root of 2. That makes it positive, and that's it right there. So this is also the same area as here. So that's area between curves. Integrate top minus bottom, straightforward. Questions? Okay.
I just have a question.
Oh yeah, go ahead, Brandon.
How would you set up the integral for region 2?
Well, let's
find region 2.
Okay. Okay. Brandon picked the next problem. So now we're going to do the area of region 2. And you're asking that because there's an issue, isn't there? So what do you think we do?
Do you add area 1 and area 3 together?
Oh, no, we're just doing this area right there. If you think this is the sum of these two, you'd have to prove that that would be true.
Okay.
You can just integrate this area. But we got a problem. Oops. If we integrate this area, we have to go from 0 to pi over 2. But the functions change color somewhere along the line. So what do we have to do?
Flip it.
Not flip it. We have to break it up into 2 pieces. To do the area of this, you would do the area from 0 to pi over 4 of the sine. That will give you half the area. So you could say just multiply by 2, but you'd have to prove it's the same. And then we're going to integrate from pi over 4 to pi over 2 under the green function, cosine of x dx. Does that make sense? We would do it that way?
Yeah, now you say it.
Yep. I'm not sure that this area equals both of those, but I am sure that the integral from 0 to pi over 4 is going to be exactly the same value as from here to here. But this way you're completely safe. And I'm not going to, we just did these. So the integral, what's the integral of sine? Integral of positive sine.
Negative cosine.
It would be negative cosine. So we have negative cosine x from 0 to pi over 4. And the integral of positive cosine is?
Sine.
Sine. It's easy to get those mixed up, isn't it? So we do sine of x, and we would do that from pi over 4 to pi over 2. So cosine of pi over 4, we get negative 1 over the square root of 2. And here's a case where 0 doesn't give us 0. The cosine of 0 is 1, and this makes it negative, but it becomes positive 1. So we get that. We put pi over 2 in here. We get the sine of pi over 2 is 1. And then we put this in here and subtract, so we get minus 1 over the square root of 2. And then we add all of these together, because this would be the area of this half, this would be the area of this half, and you notice that they're the same. They're just flipped. So the area, the answer to this problem will be 2 minus 2 over the square root of 2. And that's the area of region 2. So the moral of that story that Brandon brought up is we have the roof of this region is 2 different colors or 2 different functions, so we had to integrate it in 2 different parts. All right. Okay. Next. Next problem. We're going to rotate region 1 around the y-axis. Oops, Jakob. Oh, hang on, Jakob's coming in here. Let me just wait to get in here. Jakob, you here yet?
Yep, I'm a little late. Sorry about that.
How long you were waiting? I just happened to notice your name there. Sorry about that.
Just about 30 seconds. It's all good.
Oh, good. Okay, and I'm clicking the button now, so you can. Whoops! Wait a minute. Didn't click that button. Hold on, Jakob.
That's all right. It's okay. I'm not gonna record.
Oh, okay. All right. Okay.
Thanks.
So this question is, we're going to rotate region 1, this shape, around the y-axis. What methods can we use? What methods can't we use? So when it comes down to the test thing you're going to get next week, I'm going to ask you questions like, I won't even give a specific function, just sort of a shape, and say, rotate it around this particular line. What are the methods you can use? Why? What are the methods you can't use? Why? And so you'll answer those with some sentences. And you'll see some questions like that when I send out the practice problems later. So what methods can we use to spin this around the y-axis?
Disk.
We can use disk. Can we use anything else?
Use the shell method.
Can use a shell method. Can we use anything else? There's one left. Can we use it?
No, because there's no hole.
Right, we can't use washer. So we're spinning the y-axis, and this region is up against the y-axis everywhere, so there's no empty space that will spin around, so we can't use washer. Okay. Now, so disk and shell can both be used. Which one would be a very, very bad choice?
Disk.
Disk would be a very bad choice. Disk method would be an extra credit problem because you can do it by disk. Why, Brandon, do you think disk would be not a good choice?
The formula is just more complicated than shell.
Oh, it's even more than that. If we use disk, which way do my rectangles have to go for disk? Horizontal or vertical?
Horizontal.
They have to go horizontal. A horizontal rectangle means you're working dy. That means all your functions have to be converted to y. If y is equal to the sine of x, x is equal to the arc sine of y. And y would be equal to the arc cosine of x. Now you have to integrate arc sines and arc cosines squared. Yes, they can be done, but you really don't want to do it. And you'd have, if you did it disk, you see, like the last time, we'd have to break it into 2 pieces again. So all the rectangles here are touching the red function, but when you get up here, they're touching the green function. So disk can be done, but not nicely. In general, if you can use the shell method, it's almost always easier than all of the others. So we're going to do shell. And with shell, that means the rectangles go this way. Shell rhymes with parallel. So we are spinning the y-axis. So rho is x. And the height How tall is that rectangle? What's the height of that rectangle?
Cosine minus sine.
Well, top minus bottom, right. So the height will be cosine x minus sine of x. Top minus the distance to the top minus the distance to the bottom. Right. And now we set up the integral. So the integral is, for shell method, 2 pi. We're going from 0 to 1 because, oh, sorry, not 0 to 1, I'm sorry. 0 to pi over 4. It's the rho times the height. And that would be the correct setup for that integral. So questions about that? And at this point, we're done with this problem. You can integrate cosine and sine, but x times cosine minus x times sine, we don't know how to do that yet. We're going to learn that next week when we start chapter 8 and do something called by parts. So that's the correct setup for that integral, and that would be the answer to that question at this point. And I'm not going to put any questions on the test where you end up with an integral you can't do without telling you just stop when you get to the integral. I'm not going to let you scratch your head over things that we haven't learned yet. Questions about that? I just thought I'd throw a bunch of trig stuff in there because we haven't seen a lot of that. It's going to be coming up like real fast. All right, another question. There's a function x. And there's a function g. How would you set up the problem to do the area between those two functions? What would be your process to do that?
Break it into a bunch of parts.
Yep, well, not even really a bunch, but just 3, right? So you would integrate from A to B, right? Then you would integrate from B to C. Wait a minute, I might 1, 2, here, 2 parts. B to C. Because there's really 2 parts. There's this part and this part. What would the integral be from A to B?
F of x minus g of x.
Yep, so F minus G, that's correct. And the next one would be?
G minus f.
Yep, G minus X. From A to B, F is the top, G is the bottom. From B to C, if I had drawn it right, G is the top, F is the bottom. So that would be the answer to a question like that. Okay. All right. So there's our function. If we were to integrate from A to B, what kind of number would we get when we're done? we were to integrate from A to B,
Positive?
we get a positive number because
There's more like positive area than negative area.
that's right. When we integrate from left to right, area on the top comes out positive, area on the bottom becomes negative. So if we integrate straight through from A to B, our answer would be this positive area minus this area. So we would get a different answer than if we broke it up. If we broke it up from here to here and here to here and made this positive, that would give us total area. So sometimes you do multiply from A to B, especially if you're doing things like in physics and chemistry and finance. You want something called the total derivative. You want negative area to stay negative. That'll give you a better idea of profit, total energy consumption, total energy output. So sometimes you want that. If we were to integrate this, our answer is going to be pretty close to what?
0.
0.
Answer is going to be pretty close to 0. These look to be about the same. And that could be the right answer. So if this axis was time and the vertical axis was profit, then from here to here, you have positive profit. From here to here, you have negative profit, which is another way of saying loss. So at the end of that time interval, you made 0 money. You broke even. So sometimes you do want to integrate the whole part. But if you're looking for physical area, you can't have negative numbers. So physical area, you'd have to go from here to here, get the positive number. You'll integrate from here to here and get a negative number, and you just make it a positive number, and then you add them together. So this is all stuff sort of end of Calc 1, the first part of Chapter 7, where it's all just area on there. So just some general concept questions. Okay, let's see. So you might get sort of questions like that now and then, but you'll see some ahead of time. So exponential functions look like this. And I'm going to say that this is just e to the x. So biology majors and finance majors, among others, you use e to the x a lot. E to the x is used in formulas for when you invest money in some kind of a interest-bearing thing. Often you have something called continuously compounded interest. There's things called simple interest. So you put $5,000 in the bank at 5% interest. At the end of the year, they add 5%. At the end of the next year, they add 5%, but you get 5% of the 5%. But continuously compounded interest, you just get it constantly. The clock never stops. And so your money grows like this, which is exactly what happens in the bacteria or virus world. This is how viruses multiply in your body. Ooh, how timely an example is that, right? So bacteria and viruses go this way. 2 turns into 4, 4 turns into 8, 8 turns into 16, 16 into 32. That's an exponential growth function. So we're going to go from 0 up to the ln of 7. And our first question is, we're going to do area. How do we figure out the area of that shape?
Integrate?
Yep, just straightforward integrate. So we will integrate from 0 to the ln of 7. We just integrate e to the x. And the integral of e to the x is
E to the X.
E to the X. A lot going on under that, by the way. So I always think the E stands for easy. People see E to the X and they kind of get all tensed up, but derivatives and integrals are pretty simple. So this is E to the X from 0 to the ln of 7. So that gives us 7 minus 1. Here's another case where 0 does not give you a 0. So this final answer would be 6 squared. Well, if it's money, I guess it's $6 square. I don't really know, or square minutes or something. So that answer would just be 6. Questions on anything that just happened there? Like even the algebra stuff? Everybody all right? Haven't seen a whole lot of EDXs. We're going to. All right. Same drawing. Now we're going to rotate it around the y-axis. All right. What are the methods we can use? What are the methods we can't use?
Washer.
I couldn't understand that. What was a washer?
Mhm.
You're saying washer we can or washer we can't?
We can.
We can, but not for the whole problem, Michaela. You see what I'm saying?
Oh yeah.
I think you could use shell here.
We can use, yes, we can use shell. And Michaela said washer, and she's correct because this empty space. But look, down here, there's not empty space. So we can use washer, but not for the whole problem. We have to use washer up here and disk down here.
Mm-hmm.
Okay, so we can use disk for the lower part, and then we would have to use washer for the upper part. Which one's probably less work?
Shell.
Shell is less work. First of all, if we do disk and washer, again, our rectangles go this way. So we have this function, y is equal to e to the x. But if I turn my rectangle this way, I have to rewrite that as x equals y stuff. So how do I make that, how do I change that equation to say x equals?
You have to do the ln.
Yeah, so x is equal to the ln of y. So that's what you would end up with if you did disk and washer with the function there. So we're going to do shell, but you can use those. But it'd just be like way too much work. So we're going to do shell. Shell generally, almost always, shell is the way to go if you have a chance. So with shell, so we're spinning a vertical line. So the shell method is parallel. The rectangles are parallel to the line that's spinning. And again, we're spinning the y-axis. So rho is x, and the height of our function is just e to the x. So our integral becomes with shell 2 pi, the integral from 0 to the ln of 7, x times e to the x dx. That's the setup. Now, next Thursday, not Tuesday. Tuesday, we're going to review all the practice problems I'm going to send you. Thursday, we're starting chapter 8. The first method we do in chapter 8 is something called by parts. And this is the very first integral that we're going to do. You're going to learn how to do this integral next Thursday as the kickoff to chapter 8. It's not difficult. We just haven't gotten there yet. The answer, by the way, is going to be x e to the x minus x. That's what the answer is going to be. Don't worry about that for right now. I know some of you have seen this before. And any Calc 2 class in the world, this is the first integral you do with by parts. And we'll also do x times sine of x and x times cosine of x, as well as some other things. So this was just a setup. We didn't see a lot of e to the x lately or any kind of trig stuff. Let's see. Oh, what else? Anybody got any questions about anything?
I have a question.
Okay.
I forget, is rho like ever not x or y?
Yes.
Okay.
I'm glad you asked that. I'll do an example right now. Thank you for, I was going to do that. I forgot. Thank you. Okay. Any shell question on the test, by the way, it's always going to be vertical. I'm never going to have you do a horizontal shell. It's always going to be vertical. So it's always going to be dx. So there's some function. So shell method. Rotate around y. So rho is y. And the height in this case is just a function. And that's it. And then you just do the integral. Now, same function, but now we're going to rotate it around that vertical line, which is not the y-axis. The height is still the function, but now rho becomes c minus x. That's the only exception. So if this was a 3, it'd be 3 minus x. If it was a 1, it'd be 1 minus x. If it was 100, it'd be 100 minus x. So if you're rotating the y-axis, oh, sorry, should be x. If you're rotating the y-axis for shell method, rho is always x. If you're rotating a vertical that's not the y-axis, rho is always that number minus x, always, no exceptions. So I'm glad you asked that.
Would it make a difference if like the line x equals c was like on the other side of the y-axis?
No, then it'd be c minus minus.
Okay, thank you.
Right? Because it would be all of this plus that other bit.
Okay.
And you can always, we're not going to, so this isn't a course in like physical engineering where you really get into this stuff, right? You can always, if you don't like where it is, you can always shift things over and just say, that's the y-axis. And then you can readjust the formula and the from and to. You can always sort of move the XY axis around to make your problem easier. We're not getting into all that stuff here, though. Everything I give you is always going to be up in the first quadrant.
Okay, thank you.
Good question, though. Anybody got anything else? So we got area, disk, washer, shell, arc length, surface area. Those were the topics we did. And disk and washer are really the same thing, right? Just a disk is just a washer without a hole, or a washer is a disk with a hole, however you want to look at it. They're equivalent. What else you got? Because I'm not going to do anything else tonight if you don't have any questions. I figured there'd be a lot more homework questions. So keep doing all those. Don't let Kayla get lonely. Sign up for her sessions. Make sure you make use of her. You can email me with questions. We can meet up one-to-one. You're my last class of this week. My next class is 11 o'clock on Monday morning, so got nothing going on in between then and now. Like literally nothing going on. All right, so well, if you don't have any more questions, just go over all the old homeworks. Look at instead of just looking at just the homework in the text, page back, look at some of the examples. This guy This guy does okay with examples and explaining and all of that stuff. So take a look at some of those. Sometimes the examples in the book sometimes show up on a test. So nothing else from anybody?
This is a question not necessarily about the homework, but what resources are we allowed to use in the test?
How many what?
What resources are we allowed to use in the test?
Textbook, notes. Yeah, whatever you want. Not each other though. You can use each other for homework. So just do the test on your own. But if you got, resources, in order to correctly use a resource, you have to understand the problem so you know what to go look up, right? So that in itself is a kind of understanding.
So it's kind of like the AP test then.
I have no idea what an AP test is. I've seen questions and all that kind of stuff. So, so I know you're all worried about tests and grades. I get that. We've all been there. My concern is that you leave this course knowing more about the world than you did when you came into it. So you're all in Calc 2. You're all in Calc 2 because you've got a plan for where you want to be. You're headed towards something, right? You're on a journey. You're on a path. So nobody's probably engineering. No one's ever going to ask you to do a shell method on your job. No one's going to ask you to do disk and wash. Our computers do all that. But what you're doing here is you're learning how to figure stuff out. You've got technical information you were given and you got a problem and you got to learn how to apply the method to the problem. And people are going to be asking you to do that all the time. So when you're learning shell and method and arc length, and we all got a little bored with it, keep in mind, it's not really about shell, arc length, surface area washer. It's about learning how to figure out stuff. Because when you get into some professional or something job, someone's going to come to you and say, you got to figure out how to do this problem. No one in the world knows how to do it. You got till Friday. See you then. And you got to sit down and figure stuff out. So the more time and effort you put into figuring stuff out. So my goal is to get you learning. As far as tests go, because I don't collect homework and I don't grade it, even in a classroom, I never do that. You're grown-ups, do it. So my tests kind of are all about, have you been doing the homework? Sometimes homework problems will be on there. Problems will be sort of like the homework problems. So you might say, oh, that looks like this homework problem that I did. I think I'll try to do it that way. So that's how I approach everything. Okay.
I have a question for you, but it has nothing to do with this class. So I don't know if you want me to wait.
Yeah, I can wait. So I'm done, folks. So have a nice weekend and do a few problems every day. Just do 1 or 2 problems to keep your brain going. I'll send out that stuff tomorrow for practice, and that's what we'll do on Tuesday, okay?
So you say the practice problems will be out tomorrow?
Yeah, I gotta like dig through my old files and pull out I'm gonna send you old test questions is what I'm gonna send you, right?
Okay, great.
I gotta paste them up and put them together and all that kind of stuff. So yeah, sometime tomorrow.
Awesome. Thanks. Have a good one.
Bye. Thank you.
Have a good weekend.
Thanks.